you have to assume constant density. So you're taking systems, of random points, but with different number of points, but at constant density. Okay? And 1, and 2, and 3. So n changes, but you are at constant density. Otherwise, yeah, that would be another problem. So I want to know how the average nearest neighbor distance depends on n if you do not correct for border effects. Okay? Constant density. So you always put the same number of points. Okay. Today we'll talk about correlation. So, even though the most conspicuous feature of collective behavior, when you watch vlogs or school fish and so on, is certainly global order. So the fact that they have very high polarization is very high order parameter. I believe that what is probably the most important signature of collective behavior is not global order but correlation. Okay? And so today we'll work on a couple of tools to highlight correlation in collective behavior. In particular, when I mean correlation of the fluctuations. So before I proceed, I really need to know how much some of the concepts I'm going to talk about today are known to the audience. Be honest in answering this question. How many of you do not know what a connected correlation function is or a non-connected correlation function is? Do not know. Please raise your hand quite high. Okay, good. Thank you. So, correlation of the fluctuation. What I mean by that? What you really are interested in collective behavior, but also in physics, is not quite how your degrees of freedom are correlated to each other, but how the fluctuation of the degrees of freedom with respect to the average are correlated to each other. So at the level of collective behavior in biology, what you want to know is how the change in behavior of an individual can influence the change in behavior of another individual somewhere else in the world. So for example, we're all flying together, and then a falcon arrives, or I perceive the presence of a falcon or a predator, and then I steer. So I change my behavior with respect to the average behavior. The average behavior here will be the overall velocity of the flow. So I make a small fluctuation. And then the guy next to me makes a small change in behavior because he sees me, and then this thing is propagated even beyond the range of the interaction. So what we're saying here is that there is a correlation between the change in behavior of one individual and the change in behavior of another individual, even though they are not directly interacting with each other. So the first important thing is that then we want to know correlations of the changes of behavior, and this is what is called fluctuations in physics. Okay? The other important point to understand is that correlation is different from interaction. So again, a question. Please raise your hand if the difference between correlation and interaction is kind of blurred in your head. Okay. Good. Right. So interaction is a way to directly transfer information to someone else, to someone who typically is close to you. So it's direct transfer of information. Okay? Correlation is a non-direct transfer of information. So you interact with someone, you interact with someone else, interact with someone else, and so on. Okay? It's like in the game of telephone, you just talk to the guy next to you, but then these things propagate. Right? So it's important to understand that the range of the correlation can be higher, longer, the spatial range of the correlation and the range of the interaction. And in some cases, it may be much longer than that. Okay? So the range of the correlation, which is called correlation vector, could be larger than the range of the interaction. Okay, so correlation is due to the interaction. Of course, if you didn't have any interaction, you wouldn't have any correlation, but they are different things. So let's call psi the range of the correlation, and RC the range of the interaction. And we have seen that RC could be a function of the density in the case of flux. Okay? But so in general, you will have that psi is larger than the range of the interaction, and in some cases, psi is much larger than the range of interaction. Okay? So the span of the correlation can be much larger than the range of the direct interaction. So this is what we call the correlation length. In physics, and sometimes in biology they call this the effective perception range. And they call this the perception range. So the idea is that the perception range is really the range of the interaction. So you directly feel the neighbors that interact with them in some way. But then you have correlation, which is has a longer range, and they call this the effective perception range. And the idea that sometimes the effective perception range can be much larger than the actual perception range. And those cases are typical inputs. Okay? So how do we define now the correlation function? So the connected correlation function define it this way: Cij equal average of phi I minus average phi j minus average phi j. So what is phi here? Phi is your preferred degrees of freedom, what you're observing. It could be the position of the particles, it could be the velocities, it could be whatever you're observing in your system. Okay? Is your order parameter. So this bracket means average. Okay, and I will show you in a minute what kind of average we should do. Right? So the important point here is that this, you see, is the fluctuation. This is the delta phi of I. I is particle I and J is particle J. Animal I and animal J. Or cell I and cell J. So you see, this is the value of the order parameter minus the average value. And then you make the product of the two, and you take the average of this product. This is the definition of the connected correlation function. The non-connected correlation function, non-connected, would be phi I, phi j. So the correlation function of the order parameter, not of the fluctuation. So what is the crucial difference between these two quantities? That if the distance between I and j goes to infinity, so if the two particles are very far away from each other, okay, then you can factorize the average. Correlation always decay to zero when you go to infinite distance. So this goes to zero, right? Because the average of each one of these two pieces is zero, because you subtracted the average of it. Well, in this case, this goes to phi squared. And basically this is the polarization, is the order parameter. So this object doesn't decay to zero. So it's not very useful because, for example, in a flock, we have very high correlation, very high polarization. So if you use the velocity squared goes to very high value. The polarization goes to 0.99. While you want to have a correlation function which goes to zero, okay? Because then from this object here, you can get the C of R, where R is the distance between I and J. You can plot this as a function of R. This will decay in some range, and you can call this decay rate psi. Okay? So this is why you want to use the connected correlation function. Calculating the non-connected correlation function can be a fatal mistake in your data analysis. Okay? This part here is trivial. This is just global order. You want to subtract global order from your local order terminal. Is this clear? Yes.
So a question related to interaction and correlation. If you have two particles that are nearest neighbors, then a measure of correlations of their, let's say, displacement of position, is there a measure of how much of this correlation is indicative of the interaction between these two particles directly, and how much of it is a general coming through the feedback of the entire system that kind of correlates the position?
It's a complicated question. I think we can discuss that perhaps over lunch. Yeah, it's not straightforward to distinguish the two, but anyway they are different. Even at the level of the nearest neighbor, the amount of interaction you have with the nearest neighbor is different from the amount of correlation you have.
Yeah, but in a system where interaction is known, I think that one could probably
of course. If interaction is known, yes.
Something general is known that if interaction is not known, in that case, could you deduce at least that?
Well, in the case when interaction is not known, then you have to use some inverse technique, like the one we described the day after tomorrow, and we can try to distinguish the two, but it's not easy. Okay. Yes.
Over what domain are we averaging?
Yes. Good question. Yeah, let's go to that. So what is the average there? So in principle, and this is what we do in physics, the average of phi I should be the ensemble average. So in physics we'll be using the Higgs ensemble to average over phi. So the probability distribution over your variable phi. Now in biology, typically you never know this. So you never know what is the probability distribution. Is the right distribution in physics? Doesn't need to be the right one in biology. You don't even know what is the Hamiltonian. Okay? But even in physics, typically you don't do that. What you do in physics is actually to take the time average. And if you are at equilibrium, the time average, if you average for long enough, and if you take the number of uncorrelated configurations, should be quite similar to the ensemble average. Now, in biology, typically you can't even do that, because you are not steady state. So you have a number of frames of your phenomenon, and averaging over time normally is not such a safe thing to do. Okay? So then what you do, what you can do in biology, and what we normally do, is just to make the space average. So space average is the time average, and this is the ensemble average. Okay, so this is the only one which is accessible to us. Okay, and also it makes sense because the fluctuation we want to study here are the fluctuation with respect to what all the rest of the guys are doing. So it's the fluctuation with respect to the space average, to the group average. So this is the average over the group. Okay.
So you wouldn't mix up space and time. I mean,
no, I wouldn't. Well, it depends on your phenomenon. But for example, for starlings, you've seen that they change shape continuously, direction, and so on. So when you average over time, for example, the velocity of a starling, you just get 0. Because it's changing direction all the time. So then you're subtracting here at 0, and then you're actually computing the non-connected correlation function. So you really have to be careful. It depends on what your phenomenon is doing. If your phenomenon is just a steady state phenomenon, then you can average on time. For example, people who compute that in neural assemblies, they have a bunch of neurons spiking in time in a kind of steady state way. So then they just make the average over time. But if you have a bunch of starlings or fish or cell, a front of cell growing, then averaging over time I think is unsafe. Okay. Right, so let's go to a practical case and let's see how this looks like. So again, I'll use starlings as my lab. So what is in starling are order parameter, phi I? Well, it's just the velocities. That is clearly the most important variable. what direction they're going. Okay? So then the fluctuation here, so the phi I minus average of phi is what? Well, it's something that I call ui, which is vi minus the space average, 1 over n sum over k of dk. Okay? And this is simply vi minus the center of mass velocity, big V. So the fluctuation is simply the velocity of the bird in the center of mass reference frame. So you go in the center of mass reference frame, so now overall the flock is steady, your assembly of cells or whatever is not moving overall, and then you watch the velocity of each guy. This is the fluctuation. So I want to show you how these two fields move the screen. So the first one here, these are the velocities of individual birds, but this is a two-dimensional projection. So these are the full velocities. Okay? So this is a phi I field. And of course you see they are more or less all going to the same direction. So the only information you get from here is that you have high polarization. Then this is the field of the fluctuations. So ui, vi minus big V. So here you get some information that was not so easy to get from here. So here you see that there are big domains. Now these domains are non-trivial. The fact that here they're all together, that is trivial. That is the crucial difference between the non-connected field and the connected field. Between the total order parameter and the fluctuation of the order parameter. Okay? So we want to now to compute the correlation of this field here, because we want to get an idea of how large are these correlated regions. Okay? So for example, this is another flock. These are real flocks, not simulations. Okay? And again you see that you have big domains. Remember, this is a two-dimensional projection of three-dimensional velocity. So here when you see the small dots, it could just be going in that direction. Okay, so you may have also domain here, but you're not just seeing them because they're okay, so how do we define then the correlation function in the case? Of R, so the connected correlation function is defined like the sum over I and j of ui, uj, this is scalar product, delta of R minus Rij over the sum over I and j of delta of R minus Rij. So this is exactly this same definition, even though it may seem not to be, but it's exactly that. So what am I doing? I'm taking all pairs of birds I and j at distance r. I'm computing the scalar product of the ui times the uj. Okay? I take all pairs at distance r and I divide by the number of pairs at distance r. So to compute this is very easy. So you have all your velocities and then you bin your pairs as a function of their distance. Okay? You compute how many you have at that particular value of r, and then you just compute the average of ui, uj at that particular distance r. Okay? Right. Notice that what we have here is basically the g of r. Remember that the g of r was 1 over n 4 pi r squared, sum over I and j of delta of r minus rj. So apart from a factor of r squared, what you have down here is basically the radial correlation function. Okay. Any question about this definition?
Can you remind me how u is normalized again?
Sorry?
The u, that normalized velocity, or?
Sorry, yes, sorry. Well, you can do whatever you want, but we use normalized fluctuations. Okay, so here you divide by the norm. It's up to what you want to measure, but in this case, we want to keep separated just the orientation of degrees of freedom from the speed. I will talk about the speed later. So you can imagine that the UI all have norm 1. It's just the direction of the fluctuation which is important for us at the moment. Okay, here you have the fact that you have computed the correlation function by using the space average. You see you have the space average. Gives an interesting, well, not that interesting, but an important to remember sum rule, because you know that the integral over R of sum over I and j of ui, uj, delta of R minus Rj, so the integral over R of the numerator, okay, this integral goes hitting the delta function, so it's sum over I and j of ui, uj, and this is 0 by definition, because of course the sum over I of ui is equal to 0. The sum over whole space of the fluctuation is equal to 0. Okay? So the integral of the numerator is 0. So the numerator must have a 0. It's a function which has a 0. And so also this function must have a 0 and have a 0. Okay? Just because of this simple sum rule. So basically we are only using the fact that sum over I of ui is equal to 0. Okay, but so is this important in general? Well, not really, because what is the shape of the C of R in normal system? Let's say in the Ising model below TC. Okay, the C of R typically is something like that. It's just an exponential decay. Okay, with a decay rate that we call the correlation length psi. And the 0 is somewhere here. The 0 that you need to have because of this sum rule is somewhere hidden here. So if you check your correlation function in semi-log scale, okay, which is normally how you plot the data if you want to see that there is an exponential below, you would find something like that. So you clearly see an exponential part, and then when you have to go to 0 because of the sum rule, you just go nuts down to minus infinity. But this is enough, you know, to clearly fit an exponential out of that. So normally this is what you have when you compute the correlation function. If you do that for the Ising model, you get exactly that. Okay? So this 0 here is not really relevant. It's somewhere in there, but you don't have any problem with that. So you have enough exponential part before to actually see the exponential decay and to be able to measure your correlation function, correlation length by doing an exponential fit. Okay, so first thing that you want to do is to compute the correlation function this way, and then you plot it in a semi-log representation, and you see whether you do have a regime where the data are exponential. If you have that, you fit it with an exponential, and then you extract the correlation length from that. Okay? So this is the standard case. Now, in birds, this is what we find. So this is the correlation function. It's a function of R, and this is one flock at one instant of time. So this is just one frame, one photograph. Okay? So there is no time average here, only space average. So what you see is that there's something different from what is now below the screen. So it's something different from that. So you don't have just a clear exponential decay and then going to 0. So there is no regime here where the correlation function is consistently equal to 0. It is positive, so positive correlation, and then negative, so anti-correlation, but it's never kind of 0. Yeah, it is 0 here, but just because it's crossing through. It's not going to 0. Okay? So this is not an exponential here, of course. So if you try to, yes?
Why do you expect an exponential correlation function in this case?
No, not in this case. I didn't expect in this case. But in general, I mean, Not in this case, I don't, for a reason that will be clear later, because this is a continuous symmetry. But in general, when you don't know anything about your system, you know, assuming an exponential is, you know, normal and minimal assumption. Okay? It's a pedagogical way. So I will go to the Goldstone theorem later, but doing that at the beginning seems to be kind of bad. So, how do you extract now a length scale from this correlation function? Well, you can say, let's just take a point where this goes to crosses 0, right? Because if this is going down in this way, you have a smaller range, a larger range, and so on. So we take this point as our proxy of the correlation length. But we're suspicious because this is not an exponential clearly. But so this psi, anyway, you can show that is a good measure of the size of the domains that you have been seeing before. Okay? So the first thing we have to notice is that this psi is rather large. So this is in meters for this particular flux. So this is, I don't know, 12 meters. So the range of interaction we've seen yesterday, even though it's not metric, but if you translate it in meters, is always at about 1 meter, 1.5 meters. So clearly we're in a case where psi is much larger than the range of interaction. But how large? Well, what you discovered is this. So if you plot now the correlation length as a function of the size of your system, this is what we get in birds. So psi grows linearly with the size of the system. Okay? Psi grows linearly with the L. Now, this is something which I strongly advise to do always. Try to have different sizes of your system, right? Whatever is your system, and always plot whatever length scale you find as a function of the size of your system. I know that sometimes this is impossible. For example, if you are doing an experiment on fish, and you have a fish tank, and you only have one fish tank, it's hard to make experiment with different sizes of your system. But if you can do that, you really should do that. Okay? Because this is very interesting, and in this case, the fact that psi scales with L is telling us that the correlation function is a scale-free correlation. Okay, so here we are in a case where basically there is no length scale associated to it, and the correlation decays as a power law. And I will now prove that in the next few minutes. Scale-free is something kind of widespread, so it's not simply present in birds. Okay, so what we see from the data is that psi is proportional to the size of your system. And we can rewrite this in the following way, that psi of B of L is B psi of L. So these are trivial scaling relations that I'm going to write, but again, even that some people didn't know about the connected correlation function, probably also they don't know about the scaling relations. Where B is just a dimensionless number, it's a scaling parameter. So saying this is the same as saying that. Okay? Now let me make a mild assumption on the correlation function, so that in general I can write C of R as a function of R over some correlation length, so a dimensionless function here, and then I can have some power law corrections. So this is an assumption, but it's a very mild one. You're saying when you don't know anything about the correlation function, you have a dimensional part, which is the power law here, times a function of R over psi. So typically the correlation function is an exponential. For example, in critical phenomena, this would be e to the minus r over psi, r d minus 2 plus eta. For people into critical phenomena, this would be the general form of the correlation function. function. So a dimensionless part, which could be exponential or something else, times a dimensional part, which is a power law. Okay, just to give the dimension. And then you can have an anomalous dimension, but let me go into it. Right. So then I just put together these two things, and what I get is the following, that if I measure C of B of R, B times R, B times L, okay, by using that I get 1 over B to the gamma, 1 over R to the gamma, F of B of R, psi of B of L. Okay, just use this relationship here. I multiply R and L by a factor B. But then now here I use this relationship. Okay, so what you get is 1 over B to the gamma, 1 over R to the gamma, F of R times psi of L. So the trick is that this case with B. So the B coming out from here cancels this B. Okay? And this is simply 1 over B to the gamma of the C of R L. So we get the scaling variance of the correlation function. That C of R L is equal to B to the gamma C of B of R B of L. Scale invariance. So when you have this, when your correlation length scales with the size of the system, this implies that you have scale invariance of the correlation function. Actually, these are basically you're saying the same thing, that you don't have really a scale in your system. Right? So that the dimensionless part must be basically treated. Yes?
So you showed us some data a minute ago that showed a linear relationship between
Yes,
size.
this.
Right, okay, so that was linear, isn't it?
Yeah, that was linear, yes. Right, so this is the most important relation, but I can go further because now I can say that I take B equal to A over R, so B is an arbitrary scaling factor, and I take it equal to, this is just a dimensional constant, if you want is the lattice spacing, or is the microscopic length. So it's just a dimensional, because remember, this must be dimensionless. So this is dimensional constant, and this is R. So if I take this choice, what I get is that I have C of RL, I'm using this now, A to the gamma over R to the gamma, C of A, AL over R. Okay? And now I define, let me define A to the gamma, C of A, AL over R as a G, another function, R over L. The dimensions of this function is 1. So this is a dimensionless function. Why? Because the dimensions of G are 1 over R to the gamma, by definition. And I'm multiplying by a constant, which is a length to the gamma. So this is just a dimensionless function. And I can call it G of R over L. Okay? Because this is an irrelevant constant, and the only important dependence is here, G of R over L. So what I get is that the C of R L is 1 over R to the gamma, G of R over L. Okay? And now what I can do is to push L to infinity. So you cannot do that in your experiment, of course. You only have finite size correlation functions. But then I'm saying that your finite size correlation function, by virtue of this observation that you did, must go in this way. And so now I can ask what happens when L goes to infinity. When L goes to infinity, this goes to the G of 0, which is just a constant. And so what we have is that C infinity of R, so the bulk correlation function, the one you don't have access to, is just a power law. And this is what you mean when you say it has scale-free correlation. Basically, that you only have a power law. So the there is no exponential, no dimensional function of r. The only part that is important for you is this one. Okay, this is trivial. Okay, this looks complicated, but we are basically just trying to formalize the idea that if this grows with the size of the system, it means that you do not have an intrinsic length scale in the system. Yes?
Well, you assume that the correlation function had that form in order to get
Yes.
the scale
Yes.
So we don't know if it really does.
Yeah, no, of course, I'm a physicist. I don't prove it. I only argue. Yes. If you have any better assumption, be my guest. Okay? It's a rather general one, right? It must have a dimension. Whatever you measure things, it must have a dimension. So you put the dimensional part, and then you say, and then there is a dimensionless function. It's kind of very general.
But it doesn't have to be a power law.
Sorry?
The dimension part doesn't have to obey a power law.
All right. So you want to give dimensions how?
Well, it couldn't just be a G of R. I could use it as a general function of R.
Yeah, but I can always separate the dimensional part from times something dimensional by dividing and multiplying.
Okay.
All the dimensions don't need to come from the distance.
Yeah, well, okay. Thank you for the help. Okay, so something interesting now here is how do we get, so this gamma now is the only important parameter. How fast the correlation function decays. So scale free doesn't mean that it doesn't decay. It means that it decays with a power law. It's still decaying. Okay? So how do we get an estimate of gamma? So let's start again from this function here. Okay? And so now let's define x as r over xi. So what I'm saying is now you should plot your data not as a function of r, but as a function of r over xi. Okay? So then I call c hat, okay, the same function but as a function of x. Okay? It's the same thing by using this definition. So now the important point that the derivative of c hat with respect to x at x equal to 1, oh sorry, remember that our definition of psi is the point where this is 0. Okay, remember that the definition of psi that we gave here is that c of r equals psi is 0, okay, because we define psi as this point in this particular case. So if the c of psi is equal to 0, then f of 1 is equal to 0. Okay? So then I make the derivative with respect to x of this. And what I get is 1 over psi to the gamma, x to the gamma, f prime in x. And if I estimate this, if I evaluate this in psi x equal to 1, I get 1 over psi to the gamma times f prime of 1. I don't have the other part of the derivative because the other part would give an f of x, but f of 1 is equal to 0. So I only have that. So this function is clearly monotonically decreasing, so the derivative is negative. So what we are saying is that the derivative of your correlation function as a function of x at x equal to 1 goes like minus 1 over xi to the gamma, so minus 1 over L to the gamma. So this is good, because now we can fit this, we can calculate this from our data, and we can try to fit gamma. So this is the result. So these are several flocks now, several flocks. One instant of time per flock. We're just plotting the correlation function as a function of the rescale distance, so r over xi. So what we expect from this relation is that the derivative at the 0, so here, in 1 should flatten for bigger L. Okay? So for L going to infinity, so for larger and larger value of psi, you should get some flattening. So here we selected some flux with different sizes. So from this, what you expect is to find something like that. Okay, so the derivative should go to 0 at that point. On the other hand, this is not what happens here. So this is surprising. So the fact that it's long range is not, I agree with you, I will show that in a minute, but this is surprising. Because this is telling you that gamma is actually very small. So this is an estimate of the derivative, the slope here as a function of psi, and you see, you don't see much of a trend. If you fit it with a power law, you get gamma 0.15, but even a constant is a very good fit. Okay? So what we have is gamma, which is almost equal to 0. So not only we have a power law correlation function, so a scale-free thing, but also with a very, very small exponent. And this is strange. Okay? Any question up to here?
Yeah.
Yes.
Do you have a confidence interval on gamma?
Sorry?
A confidence interval on gamma?
What do you think?
I just wondering if you have some. I mean, it's obviously consistent with 0. I mean.
No, if you make a power law fit, yes, you can ask new plot to give you the error bar. As you know, the error bars in new plot are very unreliable. But so yeah, I don't know, 0.2 plus minus 0.1. I think we put a figure in our paper, but I would say it's really compatible with 0. But if it was 0.2, it would be okay for me. It's compatible with the data. I mean, these are kind of data that are not telling you there is some number plus minus something. These are data telling you really there is no clear trend. So be prepared to anything. Yes.
So are you taking the density into account in all these?
Well, okay, I didn't go through that. At the beginning, yes, because we would expect some topological correlation length, so we made all possible kind of correlation with the density. We didn't find any of that. So in this case, it seems really that but if you wanted this in the other side of the coin, once you have a topological interaction, that is basically also a scale-free interaction, because it doesn't have a length scale in it. So then perhaps you're not surprised to see that. But no, there is no any correlation with the...
In all this reasoning, psi is a number of third rather than...
No, sorry, no. In all this reasoning, psi is in meters, as I showed you before.
No, I know all the plots are psi in meters, but should we think of psi as being really...
No. If you try to compare with the density, you really see that at different density but same L, what matters is L. So psi doesn't change with the density, it changes with L. You have to be careful to do that, to correlate it to fixed, but we try to see that. So fixed L varying density, or fixed density varying L. Of course it's tricky because we don't have all possible density, all possible L. But it really seems that psi is related to L, not to rho. So it's psi in meters. Okay, but basically why? Because there is no psi. The only length scale is the size of the system. That is the conclusion. Yes.
Speaking of density, if you do the same correlation on the local density, you look at the fluctuation of density, and from the images you showed, it looked like it was the same scale.
Well, we did that. It's harder because the statistics is much dirtier, but if you do the correlation function of the density fluctuation, you don't find any particular interesting. You find short-range correlation and nothing of this sort. But there are reasons for that, and I'm going to show you that you have to expect this kind of correlation in the system, but perhaps not the gamma equals. So, what I'm trying to explain you now in 15 minutes is the Goldstone theorem, which so is not completely straightforward to do that in 15 minutes, but try to stay with me. Okay, for those of you who know, this is the Mexican hat, so we are going to talk about that. So, basically this is a spoiler because I'm going to tell you that we had to expect long-range correlation in this case, as someone suggested at the beginning. Okay? And the reason is the following. There is a theorem by Boltzmann which states the following. So if you have a continuous symmetry in your system, okay, for example, in the case of bird rotation, it means that they could fly in any direction and that would have all the same energy, no preference for any flying direction. So the system is invariant under rotation. The Hamiltonian is invariant under rotation. Okay? But then if you have a spontaneous symmetry breaking, okay, in our case it means that you have then a very high polarization. So of all the many equivalent directions that you had, the system selected one spontaneously. So they're all flying in the same direction. So there is spontaneous symmetry breaking. But not of any symmetry, of a continuous symmetry. Okay? Then what you have is that you have some massless mode. And you say massless mode? What is this? Okay, there are many names of these things. Or zero mode, also called zero mode. Or also say, you can say that by saying that you have long range, so scale-free correlation. So these are basically all synonyms. These are the same thing. Okay? So this looks complicated, but it's not. It's basically the physics of the Mexican hat. So who doesn't know about the Mexican hat? Not the real hat. The physics. Please raise your hand if you do not know about the Mexican hat. Okay, good. So the idea is the following. Imagine that you have a potential defined over two variables, and that this potential is something like that. Okay? Right, so in this case, your V of phi, of the vector phi, is invariant by rotation. So V of phi is equal to V of a rotated phi. So this is telling you that the problem is invariant by rotation, that your Hamiltonian, your potential, whatever, is invariant by rotation. Okay? So this is the symmetry. Okay? If the potential is done in this way, then your ground state, your minimum energy, would be here. Okay? So your ground state, phi naught, is just 0, 0. So this ground state also has the same symmetry. Because if you're here and you rotate this point, just stay there. So in this case, there is no spontaneous symmetry breaking, meaning that the ground state share the same symmetry as the problem. Okay? So nothing funny going on in that case. Now, there may be other cases where the same potential is still invariant by rotation but has a different shape. And it is something like that. Okay, this is the Mexican hat. So basically, okay, let me try to do this a little bit better. So basically now, instead of being a parabola, it's just like the bottom of a bottle. Okay? So now you have a line of ground state here, but what was a minimum before now becomes a maximum. Okay? So you see, this is still invariant by rotation. So this potential still is such that V of phi is equal to V of R of phi. Okay? Still invariant by rotation. However, what is the ground state here? Well, any of these points would be good. So now the system chooses one particular point, and this is spontaneous symmetry breaking. Of all possible directions in space where to fly, the flock chooses one, spontaneously, not because there is an external field, but spontaneously. So then, in this case, the ground state is no longer invariant by rotation. If you rotate this point, you go somewhere else. You go here. Well, actually, not somewhere else. You go to another ground state. And so this is a crucial thing. When you have the spontaneous breaking of a continuous symmetry, then the new ground state is no longer symmetric. However, that symmetry connects one ground state to the other one. And this manifold here is exactly the Goldstone manifold. And I show you now that. Okay? So the idea is that in general the V of phi, if you are in this case, okay, the V of phi can be approximated around the minimum in the Gaussian way, right? Last order phi form. So you just expand to the second order the system around the minimum. The first order is 0 because this is a stationary state, and then you have that. However, when you have this case, so this kind of thing, right? So let me see that from a so this is your line of minima. You cannot expand around the maximum, of course. So the maximum is no longer the good point around which to expand. So this is your new ground state here. So you have to expand around this point, the potential. And then clearly these are the two most natural coordinates to do that. Okay? So let's call this coordinate phi orthogonal and this phi parallel. Okay, so now your V of phi will be V of phi naught, okay, plus second derivative of V with respect to phi orthogonal times phi orthogonal square plus second derivative of V times phi parallel square plus order phi form. Okay? So this is the expansion of your potential around this point. But you see by definition that this derivative here, the second derivative, is 0. Because that is a flat manifold. Exactly because you broke a continuous symmetry. Okay? So this part here is 0. So you have two fields, two directions, but one of them has 0 mass. So this would be the mass square of this field here. So this would be the massive mode. So this is massive means that you have an inertia, so you want to go back here. So if you excite this mode along this direction, you feel a force and you want to go back there. However, along this direction would be phi orthogonal, you don't have any force. Right? And so this is telling you that the mass of this thing is equal to 0. So what is it the mass has to do with that? Well, by the way, I think this is interesting because this is really strongly related to birds and to many other systems. But once you're here, you're a few steps from the Higgs mechanism. And you'll do something which is kind of different. So I think it's a nice connection. Because if you make this symmetrical local, a gauge symmetry, then you have exactly the Higgs mechanism. But anyway, so this is the Goldstone mode. So this is the Goldstone mode. So how this is related to the correlation length? Okay. Well, you can see, and I will show this in a minute, that psi is normally 1 over n. and how this works. Well, the partition function of this kind of system would be an integral over phi of e to the minus phi, and then you have the second derivative plus m squared phi. So at the Gaussian level, I'm saying that the probability distribution of phi is Gaussian. You just make this expansion, and you have the mass term here, m squared. And this is just a gradient square, right? It's something which is telling you that the order parameter doesn't want to be distorted too much. Okay, I'm going fast here. I can't. But this is the general field theory for a Gaussian field. Okay, so this is telling you then, in the case of a Gaussian field, the correlator of the field is the inverse of that operator here, to the minus 1. Okay, but then you go to so let's call this G. Then you go G of x. Then you go to Fourier space. And the inverse of this in Fourier space is very easy. It's 1 over k squared plus m squared. Because the Fourier equivalent of the derivative is a factor k, the momentum. And then, if you make the Fourier transform of this, you get a G of x, which is exactly e to the minus x over, sorry, x times n. E to the minus x over xi. Okay, all this is to tell you that n has a dimension of 1 over a length, because it's a dimension of a length. I know this is probably you're not getting all that, but I wanted to show you that the fact that you have a mode with zero curvature here, the Goldstone mode, a massless mode, is directly connected to having a correlation function which is scale-free. Because now, if n is going to 0, psi is going to infinity. Okay? And then you only remain with the power. So basically, what I'm telling you is that in the case of birds, you had a continuous symmetry, okay? And the continuous symmetry, is broken because the flock is going in one specific direction, and then you would expect to have scale-free correlations, okay? Then the G of R goes like 1 over R to the gamma. However, there are two surprising things. First of all, as I showed you, that this gamma is very small, and this doesn't need to be the case in the Goldstone case, in the Goldstone theorem. So gamma is normally, for example, is 1 in the Heisenberg model. Okay? But there is something else which is surprising, which is the following. So this is the intuitive idea of the Goldstone theorem. So you have the Mexican hat, and you have two directions. The massless direction, the one with infinite correlation, and the massive direction, which is this one. Now the Goldstone theorem only tells you that this mode has got infinite correlation length. And not this mode. This should be the massive mode. Now what is that mode for the birds? So remember, this is basically the velocity. So this here is the rotation. So it's a change of heading of the birds. And this is what? Well, this is the change in the modulus of the velocity. So that is the change in the speed. So what the Goldstone theorem is telling you is that the speed should not be long-range correlated. Because that is a hard mode. And it's not only a hard mode in the Goldstone content, but also in a biological content, because changing your heading, your direction of motion, is clearly easier, much easier, than changing your speed. To accelerate, or even worse, decelerate for a bird is very hard. Okay? So this is a soft mode, and this is a hard mode. Okay. But then you get this, and this is very surprising. So now this is exactly the same kind of correlation function, but now not for the fluctuation of the orientation, but for the fluctuation of the speed. Okay? So you come to the average speed, I don't know, 50 meters per second, and then for each bird you compute the speed relative to the average speed. And then you measure the correlation function. Well, this is what you get in one particular flock. And then you work out the psi of the speed by this point. And then you plot it as a function of L, and you find exactly the same thing as for the orientation. So, not only that, if you now plot as a function of r over xi, you find exactly the same thing with a very small exponent, gamma. So this is beyond the Goldstone theorem. Now, you could have a normalization effect at higher orders, but not with the modulus of the velocity. You really wouldn't expect this to be a long-range correlated mode. Okay? So this is something surprising, quite unexpected. Now, what could be the reason of that? And this here I close, but I don't want to make too much philosophy. There are two ways why a mode could be long-range correlated. One is that you are in the deeply ordered phase and you are breaking a continuous symmetry. That is the Goldstone mechanism I showed you before. Another reason why you can have that something is long-range is that you are close to the critical point. So if you are close to the critical point, then you have zero mass and infinite correlation length, even if you have a discrete symmetry, even if you have a hard mode. So what is a critical point? The critical point is typically the following in physics but also in biology, that normally you have some noise. You always have some noise, which you call temperature in physics, but you have some noise. Now too much noise is clearly destroying order and is also destroying correlation. Okay? Now, if you have very small amount of noise, you clearly increase order. So very low noise means very high order. But you do not necessarily increase correlation when you have very small noise. In other words, if you have very small noise, then everybody is doing what everybody else is doing. So you have a very large behavioral inertia. So in that case, correlation is small because if you get a small bump from someone else, well, you know, the system is so much polarized, so the decision is so much taken that you don't actually change so much your state. So correlation is small. So this means that when you have noise in your system, sometimes you can have cases where if this is noise, the amount of order always increases by decreasing noise. So this would be the polarization. However, in some cases, the correlation has a peak, or it could even diverge, at a critical value of the noise. In this case, you said you have a critical point. Not only the correlation goes up here, but actually things like the susceptibility, all the response of the system to the external perturbations. So response to the system to the external perturbation is clearly connected to correlation, because if you have no correlation, you're not able to respond to an external perturbation. So the fact that we find this, it could be, but we don't fully understand it by now, that you are close to some kind of critical point. And why you should be close to a critical point? Well, because close to a critical point, you may have an optimal response to the external perturbation. But this is just arguing, it's not a proof or anything, okay? But the important point is that for orientation, you do not need to invoke the presence of a critical point. You have long-range correlation just out of the Goldstone theorem. While for speed, there is something more than that. Okay? Okay, fine. Thank you.
I was just thinking that it actually makes sense for a system to require such criticality here, because you showed movies where there is a falcon chasing the fox, and in that case you break rotational symmetry and velocities. You have this perturbing thing. So first thing is that you need to have this kind of behavior in order for the system to change direction. And second, if you measure correlations, then there will no longer be scale free. Is that true?
Yes, well, exactly. I don't know. I don't know about any other ways to get a scale-free correlation of a hard mode apart from being at a critical point, but there could be anything in biology, so I already see. So that is just one possibility. So let me make a comment on this. I want to be very careful about conveying to you this idea of criticality. And the problem is that there is kind of an agenda about that. So criticality of biological system is a very cool idea. So too cool. So sometimes kind of pushed just, out of no data. So you have to be very careful. What I'm saying here is that for the orientational part, no problem. You don't need to have any criticality. But you have a small exponent. Strange. For the hard mode, criticality could be the way. We are working in that direction, but to prove it, you have to do some math. You cannot just say, of course it must be critical, because you have to respond to the falcon. Sometimes you also write that, but I mean, it's...
So, no, but in your case you have the advantage. You see, like in one of your movies, there was a falcon coming close to the flock. So you can look at how the correlations are changing over time. And then so it will go from scale-free behavior to something that has an interaction. So you can see the symmetry.
We can't do that. We can't do that. It's not that we can monitor the correlation function while the falcon is approaching 10 meters, 2 meters, 1 meter. No, forget it. Typically, when the falcon is approaching, the flocks just go nuts, and we cannot we cannot analyze them.
That's actually one more signature of the system. Why is that criticality that it will have interactions of all kinds of stages? If they are going nuts, it's actually good thing.
Okay, I think because we're running a little bit late already, I think we're just going to take one more question. There's a gentleman here who had his hand up.
Yeah, I was going to ask if it was really obvious before the fact that you had this rotational symmetry, because you would think that maybe different directions matter, like where the falcon is or where the ground is, because down is different because of gravity.
This is a good comment. I think it really depends on the time scale. For example, if you're talking about migration of bees, well, they have to go south. But there is an external symmetry breaking there, of course. And when you see flock, I mean, the time scale over which they change direction and they do this is so short that clearly there cannot be any particular preferential direction. They could be that they want to stay over the roost a little bit, but it's not that the falcon is always there. Okay, so they just fly around, going this way, and then they go that other way. So having a magnet making them turn all the time, yes, is a possibility, but I don't think it's a very reasonable one. But there are certain external environmental perturbation, like the position of the roost, but the fact that they are pulled around by some kind of invisible magnet doesn't seem to make much sense.
Okay, so I know there were some more questions. I'd encourage you to catch Andrea at the coffee break. I think we need to get on now. So thanks again, Andrea.